It means the derivative with respect to the given structure. The given structure is the connection. Right. In the Euclidean connection that we just talked about here, parallel means actually parallel. Okay? You can prove it very easily. Parallel here is a very deep, complicated notion, but it makes sense from the point of view of differential operators. Right? It's just parallel with respect to that. This is not a vector field on this, so here gamma point means a vector field defined, a vector field defined near, let's call it X, near the curve. So what that means is that along the curve you have the velocity vector of vector field, this is gamma point. At least you know what it means in coordinates, and so on. This is what it means in coordinates, gamma point. And I write this as, and then near here, I push this vector field, I extend it here transversely in some way so that it's defined in a neighborhood. You can imagine how to do that, right? You just take transversal and then push it transversally in a neighborhood. You see what I mean, right? Right, that's good. So you extend, you can always extend this gamma point, which is only defined along curve, to a vector field X, and it means, so this equation star means simply that nabla X of S is 0 on gamma. You understand what I'm saying? Nabla of X is only defined when X is a vector field. And if you just have it along the curve, it's not even defined. So you just push it off the curve in an extended way. Right? Yeah. Okay. So, and then I'm speaking over it. Okay? And then we say S is parallel along this curve. Okay?
Question, what if the curve self-intersects?
Okay, so you have to really start to think about what it means, a self-intersecting curve. And the right curves here to consider at first are not such, but are piecewise smooth with no self-intersections. Okay? And you really, and in fact, your textbook talks, I didn't want to get into it right now, but you really need to think, because about what such a thing is. For geodesics, when you're talking about geodesics, it's sufficient to talk about piecewise smooth and no self-intersections. But just like Misha, I would like to be able to introduce a theory for any smooth curve, right? And so, so in your textbook, I checked it because I know you might be interested in reading. The author discusses admissible curves. When an admissible curve means piecewise smooth, no self-intersections. Okay, and then Misha, you understand, of course, it's very easy to push some vector field off that curve, right? Okay. So with respect to C in the text, for the notion of admissible curve. Okay. So let me just prove a theorem for you, and then we have a little pause until the next session today is given y in the tangent space at the base point. No, not in the tangent space, any vector at the base point. There is a unique vector field gamma. So y of t, which is in the vector bundle gamma of t. Let me write this here as gamma of 0 and gamma of t with, which is parallel along the curve. So that means gamma t of y of t is like that, 0. Okay? That's a first start. That's not bad, right? You give me a curve and an initial vector, and I can give you, using the connection, depending on the connection, of course, a canonical movement of that thing parallel to the other end. From the beginning to the end, parallel. Okay? This is what Riemann was feeling. It's called parallel transport. Okay? Good. Let me prove it. This is well known to you, but you didn't realize you knew. Okay. Oof. Okay. So let's let y and t, so let's prove it using a local frame first. E, say E1 through En. 4. 4. E. Okay. So we want this thing y of t should be then functions f I of t di of t. Right? So, and where the fi's are to be determined. Okay? And the condition is that nabla of gamma point of yt is 0 is the condition. You need to understand. Okay. So gamma point of t, that's a vector field, so that's the vector field x. Let's call it xi di. Well, all of this is dependent upon t as we move along the curve. So maybe I write it xi of t di of t, of course. Okay. Well, okay. So what is the condition? Let's write this as star, and let's write it out. So star is this guy applied to that guy means first you differentiate. First you get fi. Oh well, here we go again. Let's call this one is I and one is j. I knew I was going to make this mistake. Let's call this thing j, and let's call this thing I. And now we hit this thing with this differential operator, and the first thing we do is we pull out fj of t, and we apply the basic frame to the basic frame. Right? This is what's going to be the Christoffel symbol. If this for the tangent bundle, this will be Christoffel symbol. So omega appears. Yeah. That's the first thing you do, is you pull out the constant and you apply, did I do everything? I pulled out, here's y, and I pulled out this thing, that's fine. And now what I have to do is I have to differentiate this thing. So this is the partial derivative of fj with respect to di times what? ej. Right? Have I done it right? Please check me. Right? I applied Leibniz somehow, right? So I apply this guy to that guy, and what I do is, the coefficients here, I didn't even, I'm an idiot. Okay. Where? Here I need coefficients, right? xi. Right? Okay. Well, I mean, and this has to be 0. Okay. Right? No, that means it has to be 0 for all j. It means this has to be 0 for all j. Fj of t,
You're still missing xi.
huh?
You're still missing xi next to the f.
Next to the what?
So we're taking, so the connection and the vector field you just showed.
Here's the vector field,
Yeah, so the left,
and here,
overall.
I forgot the xi here again also, right?
Yeah.
xi. Okay? Right?
Yeah.
So let me write it down. So what I have to do is fxi delta I plus xi. I'm probably making a mistake here someplace, but it doesn't matter. Has to be equal to 0 for all j. Right? Because that's a basis of the vector space, so all the coefficients have to be 0. Right? Well, look at that for a minute. Okay. Notice that these are the unknowns, and this is a linear in these unknowns. This is just something I don't know what that is. And here are the derivatives of the unknowns. This is what is known as the standard ODE. So this is a standard ODE, a first order ODE, and you apply the standard existence and uniqueness of the standard ODE, which means for any beginning initial value of the functions, you have a unique solution. Well, the initial value here is y of 0. So you have the vector y of 0 in the bundle, and you push it with this differential equation, and you have a unique solution which is called parallel transport. Okay. So, and you can believe me that the other way around, parallel transport is very, very close to a connection. So you can see how Riemann was thinking of moving from one fiber to the other in the bundle. So this is parallel transport. Okay? You okay on that? Yeah. Okay. That's perfect timing to finish the lecture. So we meet again in what time? 15 after or something like that. Thank you. So I hope you can hold out these 3 lectures in one day. We'll see what happens.